Good morning and welcome to today's webinar, Printed Interconnects and RF Devices for High Frequency Applications, hosted by Optomec with special guest Lockheed Martin. I'm Shana Watson, Optomec Marketing and Events Manager. To begin, let me explain how you can participate in today's presentation. We welcome your questions and feedback, so if you have any questions, submit them in the chat window at any time. We will do our best to answer all of your questions at the end of the presentation. Please note that all attendees are automatically muted, so the best way to ask questions is by using the chat window shown here. Please also be aware that the presentation is being recorded and will be available online within the next week. Now let's meet our speakers for today. Mr. Brian German is Product Manager of the Aerosol Jet product line, including machine platforms, print engine products, as well as digital and software products. He also manages strategic customer projects centered around volume production applications for aerosol jet technology. Brian joined Optomec in mid-2017, and he previously worked for GE Power, where he successfully integrated Optomec's aerosol jet technology into production work cells for printing high-temperature ceramic sensors on heavy-duty gas turbine blades. His background in materials, process, and Optomec's core technology enables him to help Optomec's customer base working on high-volume production applications for aerosol jet. Brian currently holds 13 published patents. He also holds a BS and an MS in mechanical engineering from the University of South Carolina. And Mr. Steve Gagne is a Lockheed Martin Fellow Research Scientist for Lockheed Martin Rotary and Mission Systems in Oswego, New York. He's responsible for new product designs, R&D, manufacturing support, quality assurance, failure analysis, and materials consulting. He is chartered to develop new and emerging technology for RMS next generation electronic platforms, and he currently holds 12 patents with 2 pending and is seeking his PhD at Binghamton University, while currently holding a BS in mechanical engineering from Penn State University and a Master's of Science in Material Science from the University of Virginia. Now I'm going to turn it over to Brian German. Brian, please go ahead.
Thank you, Shana. Good morning, everybody. I want to take a moment to just thank you guys for attending this event. I hope that it will be enlightening for you and that it will generate lots of questions for which Steve and I will be happy to take some time at the end to answer for you. I'm going to take a moment to tell you guys just a little bit about who Optomec is and what aerosol jet is. Optomec is a global company. As of 2018, we have 5 locations. We just opened a new location in Singapore and in Zurich, Switzerland. And we have roughly 500 installs of our 2 core technologies, aerosol jet and lens, which I'll talk about in just a moment. And we're about 125 employees and privately held. Aerosol jet and lens are the 2 technologies that we're here to talk about. Lens, which is not the focus of this presentation, is a structural metal printing technology used for adding material to gas turbine components or repair of molds and other heavy metal components. Aerosol jet is a functional material deposition technology really focused on printed electronics, which has the ability to print everything from interconnects, which is what we're going to talk about today, to antenna and sensors, mostly focused on printing, conductors onto low temperature substrates or semiconductor materials. just a little bit about again, the core of what Aerosol Jet is. It's a contactless, fine feature digital printing process, and what that means is that we can deposit line widths ranging from 10 microns up to around a millimeter, or as thin as 100 nanometers, or as thick as several microns to 10 microns with a single pass at a very high standoff distance to the part. And this really enables the applications that you see on the right side of the screen, which are kind of our core functional areas that we operate in, which are bond wire replacements and printed conformal antenna or plastic metallization. Some of the advantages of our process obviously are the increased design freedom, the ability to kind of put material discreetly where you need it, and the ability to use lower cost materials and processes in order to create these functional devices, which we'll talk about in just a moment. Steve's going to share some really great examples with you. And we package this print engine technology into platforms because Optomec is a capital equipment manufacturer. We make machines like the AJ5X that you see on the screen here, which are tailored more towards R&D and low to medium volume production. But we also sell the OEM print engine, which can be configured into automation lines for high volume manufacturing. Again, just some more basics about how Aerosol Jet works. So we take nanoparticle or particle-free materials or even short chain polymers with viscosities ranging from around 1 to 500 centipoise. We can process materials up to 1,000 centipoise, but we have to heat them in order to lower the viscosity. So really, this is the core functional range of the materials that we can work with. And those materials are atomized into a dense aerosol. We then use a high purity gas, nitrogen in most cases, to transport the aerosol down to the print head, where we add a sheath gas, which collimates and accelerates the aerosol beam through the nozzle and down onto the substrate. And as you can see in this short CFD simulation of how that sheath is introduced, you can see that the mist is moving slower here and obviously accelerating as it's jetted onto the part. And this allows us to be 1 to 5 millimeters off the surface of the part and print onto some oblique surfaces, which we'll show here. So this is kind of the key enablement of the Aerosol Jet technology, the ability to scale the line width and to print onto non-planar surfaces and get consistent trace thickness as you traverse the print head around the substrate. And now getting into, now that we got all the introduction stuff out of the way, this is some of the highlights of our printed interconnect solution. So what are printed interconnects? They're wires that are conformally printed onto non-planar substrates, like you see in the video on the left here. And what you're looking at there is a 280 micron tall stack of thinned background memory die that are stacked in a stair-step configuration, and we're printing a 3 to 5 micron tall, 35 micron wide wire up that 280 micron staircase. And this video is in real time. We're doing it about once every 800 milliseconds or so. And this is really empowering because this is all happening non-contact at room temperature. We're imparting 0 bond force to the component, and these 8 interconnects are replacing what would be normally taken up by a stitch bonding operation. So the 0 bonding force is really valuable because it allows you to work on very fragile substrates like gallium arsenide. The fact that we're able to print these small wires and we don't need to leave landing area for the bonding capillary allows us to make the pads smaller. And because we're printing conformal wires, they're shorter, meaning that they have lower inductance, and we're able to do a better job at impedance matching with our interconnects. And this all results in smaller, thinner, and effectively cheaper packages, which again, I think I'm highlighting to Steve because I think that the examples will highlight these facts directly to you. And in the lower right-hand corner, just a highlight of the different types of conductor, dielectrics, and substrates we consider to be within the package solution of printed interconnects. The design process of how the interconnects get laid out is all done in CAD, ideally in 2D DXF files, or even with 3D CAD models with some of our other software. And we convert those patterns and geometry into printing paths that are loaded onto the machine. And then we use vision alignment to align where we're going to print the line to the pads on the surface and print the part. All of the inks that we print, whether they are polymers or conductors, are green, meaning that the particles are not centered. We have to add energy into them in order to make them functional. So many of the fillet materials, these materials that you see that the interconnect is actually riding on, are made with UV curable materials. And then we use different either photonic or laser-based sintering methods or oven sintering methods to cure the wires and make them electrically conductive on the substrate. Just a little bit about the packaging process. Obviously, stacking the die is the first step. This is the primary method that we use, especially in the millimeter wave space, just because it's the most cheap and effective. There are other scalable ways to do higher volume techniques, but dispensing or printing a UV curable fillet is kind of the standard method, and that allows us to get this transition, which we'll go over the interconnect geometry in just a moment. Then we obviously align and print the interconnects and then do the sintering operation. And we're still in the midst of trying to launch this packaging solution to the broader semiconductor packaging market. And as you can see here, we're in the midst of doing some machine platform development and packaging of the solution to deliver it to some very large customers that would be using this on real products in probably early 2021. This is just kind of outlining some of the geometry of the different types of interconnects that you might see. Obviously down here you can see a cross section where these are the die stacks that you saw on the previous video, and what we're doing is we're creating this fillet that the interconnect is then printed on to connect from bond pad to bond pad at the different levels. And obviously the stack die is the one that I've highlighted the most, but single thick die right here. So this is a limiter diode, which I'll show more examples of this later. Here's a microcontroller, a decapped and bare microcontroller die that's actually just bonded to a piece of Kapton, and we printed the interconnects right onto it. And then obviously there's a die that's been set down in a trench that we've filled around and printed interconnect there. So these are just some of the examples of how interconnects could be utilized for different package types. Most of the interconnects are going to be less than 10 microns. They can virtually be any length that they need to be, down to a 10 micron diameter bump. And the conductivity that we're going to be able to achieve is somewhere in the range of maybe 2.5 to 3 times bulk silver, which is this number here. And we're typically printing silver, copper, or gold onto nAg, nAg, or copper bond pads. This is just kind of showing some high-level HFSS simulation of printed interconnects versus wire bonds to try and showcase the signal performance improvements at a theoretical level that are achievable by using a properly shaped impedance matched printed interconnect versus a wire bond, or multiple wire bonds, or even dual compensated wire bonds that are sometimes seen inside of millimeter wave packaging. And as you can see in the diagrams on the right, the printed interconnects really, start to operate more like the transmission line or the Coplanar waveguide that the connection is being made to and from. And we simulated 2 different versions here, just a straight transition, which would be equivalent to a wire bond jumper, or we're trying to match the reference line as closely as we possibly can, and then obviously over the trench, because that's some of the applications that we have been focused on. And we thought that this data was really impactful, and it's one of the reasons I want to show you, and it's really the basis for most of what we're going to showcase today as well. So here is an example of or a physical manifestation of what we just I showed you in the simulation data. Here we've got a triquint V-pin limiter with 0.1 20 gigahertz range of 10 watts. And we printed about 28 of these samples and directly compared them to the equivalent wire bond structure that you see in the lower left-hand corner here. And the interconnect geometry, we essentially used a standard dispensing method to dispense a fillet around the bare die, and then printed the interconnect from the bond pad up onto it. Now, I want to note that we did not optimize the impedance matching capability that I mentioned earlier. This interconnect is straight. And the purpose of this test was equivalency, right? We're trying to match the wire bond capability. And I think that what we were able to show by collecting the network analyzer data here, and this data was collected in conjunction with the American Competitive Institute, or ACI. And again, the goal was just to match equivalence. And this test was very, very successful, demonstrating that the both insertion and return loss performance of these interconnects directly matches the triple wire bond configuration. Just another note on the reliability of the printed interconnect. So we've spent quite a lot of time with a large number of companies to understand the requirements associated with what these devices are subjected to, both for military applications or semiconductor, be that JEDEC or otherwise, and have the capability to do these tests internally here at Optomec. So we have some humidity testing chambers and some temperature cycling and current and thermal shock capability that we have subjected our silver interconnects on gold bond pads in this particular case to. And we're not just doing it internally, other people are also doing this reliability testing. Steve Gagne, who's going to showcase some very good results related to that. And the key takeaway is that there's really no noticeable DC or RF performance degradation over hundreds of hours of test conditions. Now, your specific application may have specific requirements, and we may have to run those tests again, but this is just to really showcase that these conformal print interconnects, with the performance benefits that they offer, are very much reliable and able to go the distance for real world applications. And I just put this slide in here just to kind of showcase all of the different literature and the different frequency ranges that are being tested with our customers that have our machines. The majority of the work that's obviously been done internally at Optomec has only been to about 20 or 30 gigahertz. We don't have the testing capability, but many of our customers do. And so as we push higher into the millimeter wave space and beyond, we will be working closely with partners to validate the printed interconnects capabilities in those frequency ranges. But just some key takeaways from these papers that were written by all these different customers, right? So the Northrop Grumman did some fairly low frequency work, stating that the printed interconnects will survive 200 thermal cycles from 65 to 200. As THD starting to push into the millimeter wave space at around 60 gigahertz, noting that bulk resistance of the wires, because we're printing a nanoparticle wire, which is inherently a little bit higher resistance than Then a wire bond would be, it virtually has zero effects as the frequency starts to climb, and that really has to do with the fact that the wires are shorter and the inductance is better than the wire bonds. Georgia Tech specifically measured roughly about 6% better performance per transition with respect to power loss. Michigan State, obviously, comparing directly with copper, and is better than really any other digital printing process with the way that we make our interconnects. Insertion losses is very similar to etched copper as we approach and exceed 110 gigahertz. And then we obviously, Michigan State making the claim, we conclude that AJ is well suited for millimeter wave circuit applications, and coplanar waveguides, conformal coplanar waveguides on ceramics, which was done by XLIM with less than 0.8 dB insertion loss. This is quite a valuable thing. And then when directly compared to inkjet, which is another printing technology which really only works on flat planar surfaces, the loss characteristics as we test this on quasi-optical terahertz devices were 1/10 that of inkjet interconnects. So I put all this up here just to kind of showcase the fact that we've worked with a lot of different customers on these printed interconnects for millimeter wave applications, and they all say the same thing, that they do perform very well, and they are reliable, and that we have quite a robust material set that we can offer to customers who are interested in doing this work. So with that, I think I'm going to pass it over to my colleague, Steve Gagne, and give him an opportunity to share with you guys what work has been done at Lockheed Martin with regards to millimeter wave devices, and with aerosol jet specifically. So Steve, go ahead.
All right, thank you, Brian. All right, so let me go back. All right, so I'm Steve Gagne from Lockheed Martin. Lockheed Martin is the largest defense contractor in the world. We have military platforms in land, air, sea, and space. I think this slide has a lot of cool pictures we normally show up, particularly when we do it for the high school kids. But I'm going to skip the extended company promo and just get right into it because there's a lot of material to cover. Okay, so I'm just having a little trouble advancing. All right, here we go. So our value proposition. So we're using additive manufacturing and direct-write printing for RF electronics. So the RF electronics for like electronic warfare, for radar, for that sort of thing, is where we can leverage the printed electronics. It's a good opportunity for our technology insertion. And we're using a hybrid approach. So we're not trying to print the entire circuit board, all the multi-layers, all the different parts of it. So we're using conventional boards on a low dielectric, like a Rogers material, LCP, quarter-ounce copper for most of the circuitry, and we're printing RF elements where it makes sense. And typically these are little 3D RF elements. And I'm going to get into specific examples of what we're doing. So we sort of make the whole thing conventionally, the board conventionally, using standard RF type of technology. And then we go in and we print specific elements where it makes sense to take advantage and get a swap reduction. And if you're not familiar with that term, swap its size, weight, and power. So in this case, it's specifically size. We can use bare die instead of packaged SMT type devices and print interconnects to the die. We can reduce the footprint versus a wire bond. We can reduce the parasitic losses of a wire bond and eliminate the tuning that's associated with wire bonds. For magnetic devices like transformers and inductors, we can tailor the device, we can tailor the number of windings to get the results we want. So it shows a lot of advantage for us, and we're designing it into our next generation electronic warfare products right now. And that's our applications: radar, electronic warfare, and UAVs. So the size is very important. We're always trying to shrink stuff down for our UAV products. So that's kind of where we're at. And I should also say we're leveraging flexible hybrid electronics. We're an active member with an organization called NextFlex that's really big in this space. And the electronic packaging, specifically 3D electronic packaging, again, to kind of get things really condensed down and save the space. All right, so as an introduction, so we did some work on characterizing the aerosol jet print on the Optomec system, and we used a pretty standard ink, a Peru ink, a nano silver ink on Kapton, and we just print these transmission lines. And in this case, we were measuring the surface roughness and the edge roughness, because when you print with an aerosol jet, you're just not going to get that nice, clean, sharp, etched copper foil type of stuff that you're used to. And that's one of the reasons why we're using a hybrid approach, because we can very easily and cheaply get a full circuit board of etched copper that would be very difficult to reproduce with aerosol jet, and frankly it would be probably more expensive. So we're doing the bulk of the printed wire and board construction using conventional means. And this kind of shows, like, the surface roughness has the 0.3 micron. That's typically what you see, and the edge roughness over here is around 4 micron. And a lot of the edge roughness is from some overspray, which if you're familiar with aerosol jet, when you print a line, the edges are not clean and crisp like etched. There's a little bit of overspray, and this profilometer kind of shows the profile, and there is a little bit of a hump and some trailing on the edges, so that is part of the profile. It's part of the things that you have to design to. So when you get into this and use this, you really want to characterize what you're printing, what your expectation is of what you're printing compared to an etched copper foil, which you might be used to. All right, and this is a little bit more of a characterization. So you can see in this SEM image of a printed line, over here on the right side, that's the overspray. So you see all this stuff here, and there's things that you can do to mitigate the overspray. And we're working with Optomec to do that. And you can see the line, it's not a nice uniform thickness. There is some trailing off on the edge. It kind of goes up to a maximum height, and it'll be that height across the width and then taper down again. So you got to kind of take that into consideration. But when you look at the structure in this fib cut, the nanoparticles, in this case it's a silver nanoparticles, it's a really nice, fine, high density matrix. That's what gives you the high conductivity compared to something like an inkjet or a screen print or some other dispense technique. You get a really nice, fine structure with very little impurities. So we kind of understood where we were going with it and what we wanted. Now this is something Brian alluded to. So we worked with Calci, University of Maryland. We were interested in just kind of like the baseline reliability of it. Now we're using it for 3D structures, so we kind of developed this little test coupon, and we have a blank coupon, a silicon blank that's about 5 mils high, 125 microns, and we aerosol jet printed these dielectric fillets. And the dielectric fillets are made from a Norland material, NEA 121. It's pretty common. It's a UV curable fillet, and it's nice because right as you aerosol spray or dispense it, you have a UV lamp right on the end, so you can kind of cure it as it's coming out or as it's deposited, so you can make these 3D structures. And in this case, we're making little edge fillets on the side of the die, so like a little 45-degree ramp. And then we would print the silver, and the silver would have these serpentine patterns that go up and down this ramp up to the top of the the silicon die, and then down to the printed wiring board and up and down. And this was our daisy chain circuit that we use for reliability. And we chose -40 to 125. That's one of our typical profiles for military use for qualification. And I'm not saying that we didn't have a few false starts with getting this and some lessons learned. But at the end of the day, when we felt we had things under control, we printed a nice print. We were getting 1,000 cycles with no failures, -40 to 125. So we were really pleased with that. And we learned a lot of stuff along the way. And we worked with Optomec, we worked with the University of Maryland, we worked with Calci, we worked with NextFlex in order to pull this off. So we were pretty pleased with this, and it gave us confidence to go ahead and actually use this on trying to build some real hardware. Because one of the things you get with the printed structures, you say, okay, so it's pretty cool technology. You can do some pretty cool stuff with it, but is it reliable? Particularly for a defense contractor where you're putting it into military environments and you have to undergo a lot of qualification tests. All right, so our first baseline into this for the RF measurements was to create a coupon, and this is a conductor-backed coplanar waveguide transmission line. So it's basically a transmission line that's going to go down the center here. It's got ground planes on either side with a row of stitch vias that connected to the bottom ground plane. We got the edge launch connectors that go on either side. And it's basically designed, it has some silver pads, and you're printing whatever you're printing your transmission line right across it. So this coupon, the substrate is a liquid crystal polymer material, fairly low dielectric, low loss. It's got a bottom ground plane, fairly thick. It's a 1/4 ounce copper on the top, and it has an immersion silver finish that we really like for this. We don't like using nAg at all for RF stuff. There's a significant degradation in the performance with nAg, so we try to stay away from that at what all possible. So this immersion silver right to the copper has been working really nice for this. We use our standard Southwest edge launch connectors. These are really nice because there's no solder, there's no conductive adhesive. You just kind of clamp them down and the pin presses right into the pad. So it's a nice, clean, dry connection with really nice RF characterization. So what we do there, we have this coupon, and we basically use whatever print method and materials we're doing to print our transmission line. And it's designed for 50 ohm impedance. So for this thickness of dielectric in the material, we're looking for a 17 mil wide line. So that's basically what we say. We send these out. We say print a 17 mil wide line, from one pad to another with a little bit of an overlap. And then when we connect the pins, we can measure the S parameters. All right. So this is an example. Now this happens to be aerosol jet printed nano copper. This happens to be a nano copper called quantum fuse that Lockheed Martin makes. So, there was a lot of interest in that. And this coupon is designed to be tested up to 20 gigahertz. That's kind of what we've been doing initially. We're obviously interested in higher frequencies for that, but a lot of our millimeter wave type of work is broadband, and it goes from megahertz up to about 20 gigahertz. So that broadband region we're interested in. So here you have the nano copper printed, the DC resistance for that 1-inch line. The coupon is you're basically printing a 1-inch line, was 0.97 ohms. So a little higher than foil copper. If this was foil copper, it would be, less than 0.1 ohms. So it was a higher resistance than just bulk copper. The trace width was a little bit wider. It was like 19 mils versus what we were shooting for was 17 mils. But when we measured the S parameters, like the S11 or return loss, where you're basically looking at the reflections from the interconnects, our stake in the ground, we'd like to see it below 10 dB, and we were significantly below 10 dB. So we were getting, almost no losses from the interconnects. Now the insertion losses, and that's probably more important to us, that's kind of the transmission line losses that you get from whatever, impedance mismatch, line roughness, edge roughness, high resistance, all those things kind of factor into this insertion loss. And for here, up to around 20 gigahertz, we're at like minus 1.5 dB, which is pretty good. That's something that we're very pleased with. I would say the nano silver gives us comparable results to that, about minus 1.5 dB type of loss at 20 gigahertz. That's good as a reference. If this was foil copper, etched foil copper, we would probably be up here between 0.5 and 1 dB. So it's not as good as foil copper, but certainly well enough for what we want to do, and is kind of drives home the reason why we're using a hybrid approach. We're not trying to build everything with printed. We're using mostly the 1/4 ounce etched copper, and then we're printing where it makes sense. All right, so that kind of baselines it. Our first application is a pin limiter diode. So we're taking that transmission line and we laser cut some pockets into it, and we drop these pin diodes. And what we're doing, we use that same NEA 121 dielectric, the printed dielectric, and we encapsulate the die, just leaving the bond pad exposed. So this is something that you kind of need a UV curable adhesive. If it wasn't UV curable, where it can kind of be cured out of the nozzle, you'd end up covering this bond pad. So in this case, we could dispense it, fill in around the diodes, but leave the bond pad clear. And then we would print a trace that kind of goes right across the transmission line to the bond pad to the other transmission line. And if you're not familiar with these limiter functions, basically below a certain power threshold, it acts just like a transmission line where the RF is just kind of like skipping over the top of the diode and goes downstream and does its RF magic. But if the power threshold gets too high, there's another Schottky diode that switches on, and then all this power kind of gets dumped right to ground. And that's one of the reasons why we have this pocket here and attach the diode right to the heavy ground plane. So when the power threshold gets high, the Schottky switches on, and all the power gets dumped, and it protects the upstream RF electronics, all the amplifiers and receivers and things like that could be damaged. So we thought this was a really nice application for it. This kind of shows some pictures of our first samples with it. So you can see the diode, and you can kind of see the bond pad, the encapsulation of the NEA 121, and then the printed silver right across it. The S parameters, again, we're looking at return loss and insertion loss, look very good. The return loss is below minus 10, all the way across up to 20 gigahertz. And then the insertion loss is pretty good. We want to stay above like minus 2 dB. So it's kind of like falling off the cliff around 18 gigahertz. So this is good at the 18 gigahertz, which we're really pleased with. Now, we've done some improvements since then to get this up. So right up to the 20 gigahertz, we really want it to be to kind of push off that cliff. So we've done some higher conductivity inks. We're working on tapering this line, because right now it's just printed straight across. But one of the advantages of the aerosol jet, you can actually taper this line and make a more of a controlled impedance transition. So in our newer samples, we've pushed this cliff out, past the 20 gigahertz. So we're really pleased, and it's actually ready for technology insertion. All right, so and again, it's not to say we didn't have some initial problems, and this was one of them. Kind of the first generation that we printed that I showed the picture of, we thermal cycled that. We actually had an early failure at 70 cycles. So this is a metal graphic cross section, and it shows a crack in the silver line right on the edge of this MESA diode chip. And so here you can see the heavy ground plane, the die attached material, the silicon chip. In this case, it's a MESA diode. Got the bond pad, the NEA-121 encapsulation, the liquid crystal polymer substrate, and then the silver ink that's printed from the transmission line to the bond pad to the transmission line. So we had that crack right there. We did a lot of analysis, did some modeling, and basically the CT mismatch and the stress riser created by the geometry was causing a high stress area there, and it was causing a fatigue crack that failed at 70 cycles. And in this case, we were cycling from -55 to 125, which when we do life testing, that's more of our standard cycle. So we 70 cycles obviously wasn't good enough. Our target was 300 cycles. So what we did, we looked at it. We wanted to print a shallower slope to kind of get rid of that abrupt transition. We tried printing a Band-Aid ink over top of where the crack would occur. We conformal coated with the same NEA-121, and we tried to print a more consistent ink thickness. So we went back for a second iteration, and we did. We achieved our target, 300 cycles, -55 to 125. And I think the big advantage was the shallower slopes of the fillet, make a nice smooth slope without abrupt bumps and ridges and all that things, make it nice and smooth in transition. And putting the conformal coat over top of the silver line, which we really have to do anyways. They're going to need some sort of conformal coating protection. So putting the NEA-121 over it, really seemed to be effective. The Band-Aid itself didn't seem to bias anything, so we've kind of abandoned that. But the shallower slopes and the conformal coat really helped, and that's what we're going forward with. And just the ink thickness really wasn't the same from the first trial, so that was just as best as we can do right now with the aerosol jet. All right, so, okay, moving on, trying to keep track of time here. So moving on to a different one, this is the direct die attach. Now, we've done a number of things in the digital world. This happens to be a TI microcontroller. So here we had an actual printed circuit on an FR4 board, and we use that same NEA-121 UV curable dielectric to print ramps all around the chip. And then we use the aerosol jet to print interconnects to the die. So you can kind of see it here. It's going from the printed wiring board up the dielectric ramp and then to the bond pads on the chip. These were normally wire bond pads. And so we're printing like 50 micron lines to bond pads that are like 150 microns in pitch. So it's really clean. We're really pleased with how this printed. And even on this board, we were actually printing resistors. So this was part of a monitoring circuit for the microcontroller, where it was monitoring a bunch of continuity circuits for shorts and opens. So we had some discretes in there, but we decided for the discrete resistors, we did also print the resistors. So this worked really well. We printed it up. We were able to load the program. It executed the program. So very, very pleased with this, and we wanted to kind of port this technology over to the bare die RF analogs. So we're kind of in the process of that, and I'll show it on the last slide that we're taking some packaged devices, getting the bare die, and putting them down, doing the printed interconnect. So we're really shrinking the footprint. When you go from a packaged SMT device to the bare die with printed interconnects instead of wire bonds, you significantly shrink the whole footprint of that device. All right, the next one is a broadband conical bias inductor. So broadband, this is something that's supposed to work from like megahertz up to 40 gigahertz. This is where we want it to be. Now we tried a few different approaches for this. Initially, we We actually printed the core with the same NEA 121 and then printed the windings around it with a silver ink, and it's kind of a two-step. So we sort of print the bottom of the windings first, and then we printed the core, and then we printed the top of the windings. And we worked I should give credit to Laboratory for Physical Sciences, Dan Hines down there. He was he really, he and his group really developed it, how to print this. We sort of told them what we knew we wanted to do, and they developed a method with the aerosol jet to be able to print this. So it was pretty successful. Now, when we printed the dielectric core, the performance was not that great. So what we did, we took an SMT component, one of these, and we harvested the conical core, the magnetic core out of it, and printed the windings. And again, Dan Hines printed the windings around the core. And we also printed this wedge, this 45-degree wedge. And the reason we do this is because the wide end of the conical inductor, that's the low frequency end. We want that separated from the ground plane as much as possible to minimize the coupling between that end and the ground plane. And the lower the frequency, the more coupling you get. So that's why we tip the low frequency end up. So when we did this, we actually got performance that was on par with the package device that's like 10 times bigger than this. So, and this kind of shows the S parameters. So the return loss, at 40 gigahertz or at minus 2.5, which was just excellent results. And I'm sorry, that's the insertion loss. And then the return loss was well below the minus 10 where we want to see. It starts just peaking up around the 40 gigahertz, the other end of the spectrum. But these were really nice results and comparable to the SMT device. So we were pleased with it. And again, we're eliminating the packaging, so we're shrinking the whole footprint down considerably versus the SMT type of packaged component. All right, coupling transformer. So here again, and it kind of use the same technology as with the inductor and LPS. Dan Hines really developed this. We kind of gave them the design and what we wanted to do. So instead of printing an inductor, we were printing a two-turn transistor. So it's a 3-port device, and I should have labeled the ports, but you got port 1 and 2, which is your normal transmission line, and you got port 3, which is a coupled line, through this transformer. And then it goes through a decoupling cap to ground, or a filter cap to ground. And it's done the same thing where you print the bottom windings, you print your core, and then you print your top windings. And in this case, using the NEA 121 worked out really nice for our coupling. We didn't need the higher permittivity of a magnetic core. This neat polymer core for this application worked really nice. And the swap advantage of this, as far as the size, is pretty significant, because traditionally we're using an edge coupler on a printed wiring board. So we're etching these lines in a printed wiring board, and when you're coupling it is just along the edge. So you need a lot of edge to get enough coupling. So in order to do equivalent in this transformer, we shrunk it down around 20 times. So the edge coupler is like 230 mils. And the printed transformer, the coupling transformer, is 20 mils. So to get the same performance, we shrunk this down by 10 times. And on these RF circuits, that becomes important, because we're trying to shrink this down, and these typically go into channels, and you have like hundreds of channels in the system, so you're shrinking it down for each channel, and it really adds up. Right, and this kind of goes through the performance versus what we modeled, and I'm going to kind of skip over this because we're already at 10 above the hour, and I want to leave like 5 minutes for questioning. But the performance was really good. We went through a couple iterations. We're going through another iteration now. We're not quite to where the modeling performance is, but we made significant improvement between the first prototype and the second. We expect even better to the third and get closer to the model performance. So we can achieve something close to the model performance. This is something we can start really designing into our products, and we actually have some prototype cases that if we can get it to work and prove its reliability, will go into our next generation products. All right, this is a MIS cap. So this is a capacitor that's used at very high frequencies. Your typical multi-layer ceramic capacitors, SMT capacitors that you get with the two N terminals. You get above like 10 gigahertz, certainly at 20 gigahertz, and they just end up crapping out. So when you're doing high frequency, we have these MIS caps, these like planar caps, and typically they have a wire bond to them. So they're soldered down, have a wire bond, but the wire bond has a larger footprint. It's got some parasitic inductance losses. So we said, well, if we can print that connection and get rid of these problems, that would be something that we could add, because we use these MIS capacitors all over the place, in our RF designs. So this was our first trial at it, and we're pretty pleased. So here shows an insertion loss curve, up to 20 gigahertz, and the typical surface mount that probably a lot of you with the end terminations and the multi-layer ceramic, you can see the insertion loss. You're up at 20 gigahertz, and you're, minus 1.4. Now, using the MIS caps with the printed connection versus the wire bond. So here it's comparable to the wire bond. Has a smaller footprint than the wire bond, but comparable performance. And here's a picture of it. So you have your capacitor, printed dielectric, again, the NEA 121, and then the ramp. So on this third one, we're trying to make this ramp extend out a lot less. So it's going to be more conformal, just a little ramp down to the pad, really shorten up that length, minimize the material, and we're trying to get the printed interconnect close to what just a straight through line. So if this was a through line without any capacitor, this is what you get. So this would be considered as best that you can do. So we're thinking on this third iteration, it's going to get even better than this, and it allows us to start putting these into our products, and we can print it along with a number of other components, and shrink the print down, eliminate the tuning. Because typically when you do wire bonding, you have to kind of tune the wires to kind of get rid of the resonance. So you eliminate that. All right, and then just the last couple of slides of some applications. So here we actually worked with GE on this one, and Binghamton University. So this is an aerosol jet. It's a 4-element, 12 gigahertz linear array receiver. So you have these 4 patch antennas. It's on polyimide, so it can kind of bend around a right angle. And then you have the receive circuit. And you have the whole RF chain where it comes in, and you have the RF out on the connector. So the entire circuit was printed. Now this was geared for surface mount. So all the parts here are packaged devices, surface mount devices. And like you look at this guy right here, which I think is an LNA, the packaged device. The actual chip is just would just be kind of right in the center here. So you can imagine if you just had the device itself with printed interconnects, you could significantly shrink that down. So we assembled that. The assembly, went okay. We had some interconnections issues, so we're still trying to get good data from the antenna lab testing. But for the most part, it printed nice. We did the pick and place. Again, we had some interconnection problems to the device that we're trying to sort out right now. But when we do that, we'll get this into the chamber and do our antenna testing. So here where I work, we have a complete anechoic chamber. And do all the pattern testing, the RF pattern testing. All right, and this is my last technical slide. So this is what we're planning on doing. So we have all these really cool RF elements that we can print. on a hybrid board. So we're putting these into a real RF chain, and this happens to be a millimeter wave receiver channel. And we actually would like to put this on a multi-chip module, because this is a very common channel, receiver channel. And a system, as I said, might have hundreds of channels. So right now, when you look at the RF chain, these are all packaged devices, and the whole thing is like 3 inches. So if we can convert most of these to bare die, plus use our MIS capacitors, with the printed connections, the transformers, the inductors, the things I talked about, and add those in there to shrink it down further, we can shrink this down, we believe, to around 2 inches, maybe less. And you're thinking, well, 3 inches to 2 inches, so sounds like a lot, but it's an inch. But when you're talking about hundreds of channels in these RF systems where you can shrink it down and you can now fit them into smaller spaces, make the whole system smaller, you can fit them into UAVs or to other places where it would be difficult to fit on helicopter platforms or something. There's a lot of advantage, a lot of interest. We're always trying to shrink these electronic warfare systems down smaller and smaller and smaller and smaller. And this is our roadmap to get it smaller. Going to the bare die and the printed RF components. All right, so got about 5 minutes left. So I'm just gonna, in summary, we're using aerosol jets, Optomec's aerosol jet. So we're printing the RF devices, the bare die level packaging with the printed interconnects, a lot of RF type of elements that we can print on there. But again, we're still using the hybrid approach where we're using conventional manufacturing to make the RF board, and that's just printing the RF elements and the RF structures where it makes sense. And I didn't get into it in this one, but we've done a lot with the antennas, printed antennas. I kind of touched on it on that last one, but we've done a lot of 3D type of antenna stuff. So that's something else. There is only a few cases where there's actually an advantage of using the 3D printed antennas versus conventional approach, but that's becoming more and more prevalent as people are realizing the advantage of printing on true 3D structures that would be difficult or even impossible to make conventional wise. So we're leveraging the aerosol jet printer for the RF, the swap advantage. We're printing 3D structures, and right now, we're trying to build up the real RF chains and prove the reliability. Reliability is a big hole in the tent before people and programs will start using those. And I think that's all I really have. So I think I'm gonna hand it back over to Brian or Shana and wrap this up. So thank you very much.
Thank you, Steve. We do have a few questions, so now we'll begin our Q&A session. I'm not sure that we'll have time to answer them all, so if we don't, we will follow up with an email with answers to all your questions in the next couple of days. If you would still like to submit a question, please click on the chat window and submit it there. Our first question is, what is the current carrying capability of these printed wires, and how much does the fillet reduce the current capability versus solid bond wire, gold, copper, et cetera? I think that's a question for you, Brian.
Sure. Yeah, thank you. It's a very, very good question. As I mentioned, we're printing nanoparticle inks, so the resistivity of the material after the sintering process is higher than a bulk wire. So the cross section definitely matters, and the uniformity of that cross section will impact the current carrying capability. The wires that are printed can observe some ohmic sintering at higher resistance measurements, and we get around that by taking the package itself up to a high enough temperature to get the full sintering of the ink. We don't have the data in this presentation, obviously, but if you get with me offline, we can show you what we do know. We do have to sinter above a certain temperature in order to get that current carrying capability. And we have to try and keep the transition with the fillet as smooth as possible so that there's no sharp corners or edges that might decrease the cross-sectional area in a certain portion of the wire. So can't really get into the specifics of how much current because it's too dependent on the cross-sectional area and the length of the wire and the amount of current being applied, and then also the max temperature limit of the package.
Okay, thank you, Brian. I think we just have time for just a couple more quick questions. Brian, you said zero bonding force. Can you comment on the actual forces since the ink has a certain mass speed when hitting the surface?
Sure, absolutely. So the aerosol droplets, remember we're printing aerosol droplets, not solid metal. The aerosol droplets have a loading to them, the amount of metal that's in there versus solvent and other stuff. And most of the inks that we print, the droplets have a density of around 2. And they have a diameter of about 2 microns, and they're moving in anywhere between 20 and 100 meters per second. So it becomes pretty easy to calculate exactly how much force a 2 micron droplet will impart on the substrate. It's not measurable with any technology that we have available to us. So we might be able to come up with a theoretical number, but that's about as good as we'd be able to quantify.
Okay. Let's see, we'll do 2 more questions and then we're going to have to wrap it up. So next question is, how many of your 500 installations are for commercial production versus university or R&D?
I would say it's probably 80-20, 80 being R&D. Typically companies will buy a piece of equipment to do development on, and then scale a process to production either by buying more equipment or transitioning that piece of equipment into light volume production use.
Okay, thank you, Brian. We have a question for Steve here. Steve, what do you think is the best way to control the surface roughness of silver ink in printing CPW?
All right, so like the surface roughness, the edge roughness, I mean, that contributes to the insertion loss. Ideally, we're trying to get as close to an etched copper foil as possible. So, one of them is, using conventional printed wiring boards. So the surface is really smooth, the substrate surface. So that really helps because that's primarily where the RF energy goes along that surface because that's closest to the ground plane. So using conventional substrates really helps. As far as printing, the aerosol jet gives you a really smooth finish compared to just about any other printing technique out there that will give you kind of a rough and irregular surface when you look at it on the microscope. Probably the edge roughness is by far the factor we're most concerned about, and the overspray. And we've been working with Optomec and other people who print this, trying to minimize that as much as possible. And some investigators have even gone so far as to kind of like laser trim their lines, and they get a measurable increase or improvements in the insertion loss. So for aerosol jet, start with a smooth substrate. Aerosol jetting gives you a nice smooth finish with the nano inks, and it's kind of technique to minimize the edge roughness, or possibly a secondary technique. But I will say, because I was talking to Brian about this, we found that probably the dominant factor is, as simple as it sounds, is the DC resistance. So when we'd used different inks and different techniques, the first thing we do is just measure the DC resistance. And although it's not a hard and fast rule, but if you kind of plot these insertion loss versus DC resistance, they track. So the higher the resistance, the more loss you're gonna get. So trying to use an ink and a sintering technique to give you the lowest DC resistance is gonna do nothing but help you.
I'd also like to just add on to that comment that there are other capabilities with Aerosol Jet that help that DC resistance problem, which is, you can print multiple layers. Increasing the thickness of the wiring, lowering the end-to-end resistance is the most surefire way to help that equation. So you can print multiple passes just by running the toolpath multiple times. And also there are other techniques to drive the resistivity of the inks down. One other comment on the overspray that I'll mention, just because I think Steve's answer was very, very well put, but we do have a lot of flexibility with how the materials are formulated, and there are capabilities built into the print process that allow us to help to mitigate that. So while a lot of customers maybe are not quite experts on reducing overspray, working with Optomec on material selection and the solvents that are in the inks can help swing that equation in the right direction for you. We've seen inks that have very, very little overspray, and some that have very poor overspray. It's a matter of printing process setup and the ink specifically that's being used.
Okay, thank you, Brian. All right, we've come to the top of the hour, so we're going to conclude today's presentation. Please do remember that the webinar will also be available for on-demand viewing in the next week, and we will send out an email with that link. We'll also be sending out an email with answers to questions that we didn't have time to get to today. On behalf of Optomec, I would like to thank Lockheed Martin and Steve Gagne, as well as our own Brian German. Thank you all for joining us and have a great rest of your day.
All right, thank you.
Thank you.